Hello everyone, welcome to C++ Quant Dev Fundamentals series. Today we are taking a look at C++ standard template libraries std list. It's not a video about how to use list, but about what std list actually becomes once your code hits real hardware. In low latency systems, the C++ standards complexity guarantees are not the main constraint. The dominant constraints are memory layout, cache behavior, allocator interaction, and tail latency. The std list looks attractive on paper because it gives you constant time insertion and erasure, stable iterators, no reallocation. But once you examine its runtime structure, how it allocates, how it traverses memory, how CPUs actually execute it, you realize that almost all of those properties are orthogonal to performance. In this video, I want to study list the way low latency engineer would, not from big O notation, but from cache lines, pointer chasing, TLB pressure, and allocator behavior. We will look at what a list node really looks like in memory, why iteration is fundamentally hostile to modern CPUs, and why most list operations destroy determinism, and why one operation, splice, survives as an exception. If you write trading systems, market data pipelines, kernels, or any performance critical infrastructure, this is not optional knowledge. Understanding list properly is a prerequisite for understanding why intrusive lists exist at all. Coming to the node structures and the real meaning of what list is at runtime. The standard list is defined abstractly. It is a bidirectional sequence container with stable iterators and constant time insertion and erasure. For low latency systems, however, this definition is almost irrelevant. What matters is not the asymptotic complexity promised by the standard, but the physical structure that is taking in memory. At runtime, list is not a contiguous block of elements. It is a graph of heap allocated nodes, each node living in an arbitrary location in virtual memory connected by raw pointers. Therefore, traveling through the list means repeatedly dereferencing the pointers whose targets the CPU cannot predict in advance. This single fact dominates every latency characteristic of the container. To reason about this concretely, it is useful to write down the conceptual node structure that all mainstream implementations converge on. So on the left side of the screen, you can see template type name T, struct list node pointer prev, next, and a value of type T. Even though you cannot rely on this exact layout portably, reasoning in these terms is accurate enough for the performance analysis. Take a look at this. On a 64-bit architecture, the two pointers alone consume 16 bytes. One is for 8 bytes and the other is for 8 bytes. So total prev and next will consume 8 bytes each. Once the payload T is added, the compiler may insert some padding to satisfy the alignment requirements. On top of that, the allocator typically stores metadata adjacent to the allocation, the size fields, free list pointers, or debugging guards. To make this concrete, consider the following experiment, which does not inspect the list node directly but helps intuition around the cost of pointers and payloads. A small payload will have only one integer of x. A larger payload has a 32-bit char, and this printing the size of function of the smaller and larger payload will give you the size of how much essentially your entire one list node is taking. In practice, even a list of integers often ends up consuming a full cache line per element. This matters because modern CPUs do not fetch individual objects, they fetch cache lines. Modern x86 CPUs operate on cache lines that are typically 64 bytes wide. When the processor accesses any byte in memory, the entire cache line containing that byte is loaded into the cache hierarchy. If a list node occupies most or all of a cache line, then accessing a single element forces the CPU to load a full line that contains nothing useful beyond that one element. There is no spatial locality to exploit. In contrast, a std vector packs many integers into a single cache line, allowing the cost of fetching memory to be amortized across multiple elements. This difference has nothing to do with big O complexity, it is purely a consequence of memory layout. Iteration, pointer chasing, and the collapse of prefetching are some other factors we need to look at about list. You consider a simple traversal, where from list.begin to list.end, we are iterating. At the machine level, this loop repeatedly loads a node, reads its next pointer, then dereferences that pointer to reach the next node. From the CPU's perspective, the address of the next node is effectively random. Hardware prefetchers, which rely on detecting regular access patterns, cannot predict where the next access will be. This pattern is known as pointer chasing. It forces the processor to stall on memory accesses far more than even in contiguous data structures. Even if all nodes fit into the last level cache, the inability to prefetch causes latency to balloon and, more importantly, to become highly variable. The impact of STD list is not limited to caches. Because nodes are individually allocated, they tend to be scattered across many virtual memory pages. Each page translation must be cached in the translation look-aside buffer, which is also called TLB. When traversing a sufficiently large list, TLB entries are evicted and page table walks occur. TLB misses are particularly damaging in low latency systems because they contribute disproportionately to tail latency. They may be rare, but when they occur, they add dozens of cycles of delay, precisely the kind of occasional spike that low latency systems are designed to avoid. Every insertion into a STD list allocates a new node. Look at the code in the right side, lst.pushback42. It is allocating a new node in the heap and creating those next 10 prev pointers of 16 bytes and then storing the number 42 in the value. So heap allocation is not a constant time operation. Its cost depends on the allocator state, sometimes fragmentation, and sometimes synchronization. Over a lifetime of a long-running process, allocation behavior becomes increasingly variable. For systems that care about deterministic latency bounds, this variability is unacceptable. Even if average allocation time is small, worst case allocation time grows over time. This is why low latency systems strive to eliminate allocation and deallocation from hot paths entirely. Most STD list implementations use a sentinel or dummy node. This node does not store user data. Instead, it simplifies the internal invariants of the list. Conceptually, the structure looks like this: sentinel to node 1, node 2, node 3, and then sentinel. When the list is empty, the sentinel's next 10 prev pointers refer to itself. This design eliminates the need for null checks and allows insertion and removal to be expressed as a fixed set of pointer updates. Understanding this structure is essential for understanding how splice works. Coming to splice. Splice is basically structural modification without touching memory. The most important operation provided by STD list is splice. The standard defines three overloads: void splice iterator, other, void splice iterator position, other and another iterator, and void splice position, other, first and last. All three share a crucial property: they modify the structure of the list without touching the stored values. No constructors are called, no destructors run, and no memory is allocated or freed. To see why this is powerful, consider the conceptual pointer operations involved in splicing a range first to last before position. So what do we do here? We detach the first last from its current list. So first prev next. So whatever is the first element in that entire list, we go to its previous one, and then we change the next pointer to last. And we go to last prev, and we make it as first prev. And then now this range which we have disconnected, we attach it to the range before the POS or the desired position. So take a pointer called before and store the value of post prev to it, and then the next pointer of that should be made as first, which we already know, and the first prev can be set to before. Now last node is taking the last prev, and then the next of that last node is again POS, and POS prev is the last node. So we successfully detached the first last from its current list and attached that range before pos, right? That is what splice is doing in big O of one time. And this is the best use of list. If you want to use list splice, that's perfectly okay. But for other things, list takes up a lot of memory. The exact details vary, But the key idea is invariant. A fixed number of pointer writes independent of list size. From a hardware perspective, this is truly constant time. After a splice, all iterators, right, references and pointers to the moved elements remain valid. This is an official strong guarantee in C++. This holds because nodes are never reallocated or destroyed. Only the links between them are changing. This guarantee makes splice uniquely suited to ordering problems where elements must be rearranged frequently without invalidating references held elsewhere in the system. We can use splice for LRU cache. A classic example is that where you promote an accessed element to the front of an ordering list depending on what is the most recently used and what is the least recently used. This operation will perform no allocation, no deallocation. It will touch a constant number of cache lines and preserve the iterator validity. From a low latency perspective, this LRU cache using list splice is an ideal operation. The only problem, however, is asymmetry, promotion versus eviction. So when promotion via splice, in the sense when you want to promote something uh, using the LRU cache, it's constant time. But inserting a new element, allocating a node, and evicting an old element, that is going to deallocate and allocate. So order.pushFront is allocating and order.popback. So inserting, deleting is going to do allocation, deallocation. So this creates a fundamental asymmetry because the common case is fast and deterministic, but the less frequent case is slow and unpredictable. In latency systems, such asymmetry often leads to rare but catastrophic latency spikes. Other STD list operations and their low latency implications like insert, emplace, pushFront, and pushback, they all allocate memory, and therefore they inherit the allocator unpredictability. Erasure operations such as erase, popFront, and popback trigger deallocation and suffer from similar issues. Traversal heavy operations like remove if, remove, unique, sort, merge, they all deserve spatial caution. Although they avoid copying payloads, they combine pointer chasing with full list traversal, making them expensive and highly sensitive to cache and TLB behavior. In low latency code, such operations are almost always unacceptable on hot paths. Once the behavior of STD list is fully understood, the intrusive lists become obvious. By embedding linkage pointers directly into the payload object, um, intrusive lists eliminate per node allocation and give the programmer full control over memory layout and lifetime. This preserves the key advantage of splice, the constant time pointer rewiring without allowing any allocator induced jitter. For this reason, intrusive lists dominate in low latency trading systems, kernels, and other performance critical environments. STD list is not slow because of poor implementation or outdated design. It is slow because it encodes a memory access pattern that conflicts with the realities of modern hardware. It's one of the genuinely low latency operation of splice. It demonstrates how perfectly constant time structural modification can be done, but it also highlights how much unnecessary overhead a standard container can carry. And a low latency engineer does not ask whether list is big O of 1 or not. They ask whether it is predictable, cache friendly, and allocator free. By those criteria, list is almost always the wrong tool, and understanding exactly why that is existing is a foundational step towards writing better systems code. And that's why in this video, when I've explained about why list is almost never really used except in cases where you need list splice, next video I will be explaining in detail the implementation of LRU and intrusive LRU using list splice, and will be benchmarking the details, the allocator impact, the costs, and the P50 versus P99 latency differences. Thank you.